Okay, so hi everyone. So we are going to finish this vector field stuff today. So one of the things we defined was for a vector field F. So I use different notations. For example, AI plus BJ plus CK. So a vector field So one of the concepts we defined was divergence. We had at least two notations for this. This was divergence of F. So this is equal to dA dx plus dE dy c dz. Right. So vector fields that had the property that divergence of F equal to 0, we named them to be incompressible vector fields for reasons that incompressible or source-free vector fields also. We called it by this name. In your book, actually, I just noticed there is yet another name for these vector fields, which is quite correct. It's called magnetic fields because of Gauss's law of magnetism. This is called magnetic field. I'm just saying in case you come across this term in your book, notice that we discussed. Of course, we discussed Gauss's law of magnetism last week, but officially it's also in your book, magnetic field. Okay, so these are the ones that we have. And one class of such vector fields we noticed you can easily construct by doing what? To construct a vector field that has this property. It's kind of difficult, right? Because you have to take three functions and do these operations on them and then put it equal to 0, and then you have to find the correct ABC. Not all ABC satisfy this equation, of course. So how can we easily construct vector fields that has this property that divergence is equal to 0? Oh, so this is divergence of equal to 0, by the way, so I never wrote it, sorry. How can we construct quickly such vector fields without,
curl vector fields?
Yeah, if F happens to be curl of another vector field, this is guaranteed. We check that, right? So, e.g., if F is equal to curl of G, this is really curl of G for another vector field G. Then we check that, in fact, divergence of curl is equal to 0. Then since divergence of curl of F equal to divergence of curl of G equal to 0, then this vector field F is divergence free. So this vector fields that are curl of another vector field, they are always divergence free. They are source free. They are magnetic. But I also said that the converse need not be true unless there is some topological condition that's satisfied on the domain. And in fact, in your book, again, I noticed that for the plane gives you the condition, which is right condition. Actually, he uses the word simply connected. So I was afraid of using this word, but your book is brave. So they already talked about it, I suppose, in some sections, and so they use that. So that's okay. But we don't heavily rely on that topological context. So I don't expect you to detect what domains are simply connected, what domains are not simply connected. Although with some experience you can, but I don't rely on that. So this is a bit of good news, maybe. I have to. Okay. So any questions in home audience by any chance, or no? Okay. So that's that. Then I said that I'm going to also discuss the meaning of curl itself. What is the meaning of curl? Okay, so the meaning of curl of F. What is it that it measures? What's the meaning of this operation, curl of F? Oh, there's a weather warning. Warning. But there is something else. There's about fishing attempt at best. This is no news. Happens all the time. So, sorry. Yeah. Anyhow, so meaning of curl of F. What is the meaning of curl of F? So to understand the meaning of divergence of F, we relied on an integral theorem, right? We had an integral theorem. I had to tell you about an integral theorem. That if you believe in that theorem, that was the divergence theorem, then I said that, well, then this really makes sense. Incompressibility, being source-free, and these things really make sense if you believe in that divergence. The same, also, there's a parallel story here. If you want to understand the meaning of curl of F, I have to tell you another integral theorem. And once you believe in that integral theorem, then you see that the curl has a meaning. Right. So what is that integral theorem that we are going to rely on, right? So the integral theorem is called, I don't know what's it called actually. It's called maybe circulation theorem or curl theorem, I don't know. Maybe Stokes theorem, circulation theorem. So the circulation theorem says this. Take a kind of piece of surface, and then you have some boundary for this. So take kind of your favorite hat. This hat doesn't have to be our CMP hat. Any, or sombrero or anything. It could be any kind of hat you want, right? Take your piece of surface, which has some boundary. Okay, so this boundary, I call it gamma. Then this circulation theorem is the following. It says that, so this is the surface itself I call S, and this is the boundary of S, is this curve gamma. So the theorem says that integral of over gamma, just to make you happy, I just put the signs. Okay. So this is this circulation of this vector field along this path gamma. Well, I mean, we have got this curl of F. I mean, curl of F, yes. Dot dl is equal to, well, I just put double integral again to make you happy. Double integral sigma or S. Well, in this case, we have got flux of F. Okay, so there is this vector field F. So this is equal to F dot dc. So you should read it in the following way. I mean, the result says that flux is equal to circulation of the curve around this. So this is flux. Flux of your vector field is equal to circulation. Actually, it's the other way around. I'm sorry. It's F dot dl, circulation, yeah, is equal to, when you take the curve, and then you do PCB. So this is the result. So this is the result. So what does then this is trying to tell us? So imagine the curl of a vector field is 0. Okay. So you'll be reading this theorem that I don't prove it, but in next term you will prove this or give an idea of why this is true. So the corollary of this circulation theorem is this. So is that if curl of F is 0, right? If by any chance curl of F is equal to 0, then the circulation of this vector field is 0, or actually along any curl circulations, right? Then circulation is equal to 0. So, I mean, the idea of circulation is that how much this vector field is moving around, circulating around this path. And if this curl is equal to 0, then this is 0. If this is true for all surfaces and for all boundaries, then you can just convince yourself that this is going to be true independent of even integral sign. So inside has to be 0. That's not difficult to see. So this is a kind of idea that curl of F measures the amount of circulation of the vector field at a point. Okay. So the general idea has emerged that so curl of F, sorry, this basically measures the circulation or amount of rotation that's given by this vector field. So that's equal to amount of rotation. In the vector field. So those vector fields that has 0 circulation, they're called what? Irrotational, or rotation free, but they're called irrotational. So curl of F equal to 0. Such vector fields are called irrotational. Irrotation. Rotational vector. So this irrotational vector field, don't confuse them with irrational vector fields. Don't call them irrational. It's kind of, they're close, but they're very different terms. Irrotational means that there's no circulation, no rotation in the spectrum. Irrational is a totally different concept. So with this, basically, I think we have now come to a good understanding of different types of vector fields and their kind of properties. So let me now give you an example of some vector fields that might be. Any question about this, by the way? No? Questions? No. Okay, so let me now give you one example. Check that vector field so f of x and y. So I just write it as, so let me do a secret calculation for myself. So this is, okay. All right. Yeah, x cubed minus 3y squared x. X cubed minus 3 y squared x I plus check the vector field J for being divergence free or curve free. I mean, oh yeah, divergence free and being curve free. I'm not saying they are. I didn't say they are. I'm just saying check them. Check if they are divergence free or curve free. Yes. But this is a kind of open question. Right? So solution. Okay, one thing you have to notice is that this vector field doesn't have a third component, right? So this vector field has just two components. But is there anything we should do about the third component? Should we worry about that or should not or what? Does it matter at all that it doesn't have a third component? We put it equal to 0, for example. We can assume it's equal to 0. So the k component is equal to 0. And what about that? There is no z here. Doesn't matter. It's like, so what is the kind of type of image, I mean, so of this vector field you can have in mind? So this vector field is like this. You draw it in the plane first as a two-dimensional thing, then they are kind of stacked over each other. It's completely parallel as you go up along the z-axis, right? As you go along the z-axis, it doesn't change because there is no z dependence. So parallel to itself moves along the z-axis, right? So it's a parallel vector field to itself along the z-axis. But otherwise, it's just fine. So let's compute now curl of this guy to start with. By the way, what do you expect, without doing any calculation, what do you expect to be the form of curl at the end of the day? Can you say something about the form of this curl? Huh? Yeah, polynomial, that's reasonable, yeah. But as a vector field, is it going to be on xy plane or along the z-axis or what? Oh, okay. So now you're saying that, yeah, the vector field is along the xy plane, So the curl should be also along the xy plane. That's what you're saying.
I think it's going to be on the Z.
It's going to be along the z axis, indeed. Yeah. So these are good things to know because you know, sometimes you write down that determinant, you make mistakes. I mean, it's very easy to make mistakes. But if you have this sort of checks and balances before, then you know that I have made a mistake. I should go back to calculation and check that. That's not. So indeed, so this is no matter what is going to be 0i. I didn't check it, but I'll tell you it's going to be 0i plus 0j plus something times k. This is the general form of vector fields that are planar. Okay? So what I'm saying then, in other words, is that i.e. for a planar vector field, the curl is always along the z-axis, has no xy component. So that sounds actually counterintuitive because if you have something which is on the two-dimensional plane, why the curl should not be leaving the two-dimensional? No, you have to leave this plane and go to space in order. And this is like the idea of angular momentum, for example, and angular velocity. That's a vector that's orthogonal to the plane, as you learn in physics. Anyhow, for a planar vector field, curl is always, I tell you, is always along the z-axis. That's a good thing to know. Now, what amount of z-axis component it has, we'll find out. And so the question is it zero actually or not? The two components are zero. Now we have to understand the term. That's what we have. So that's what we have to do. Okay, so let's do the calculation now. So curl of F. Calculation is I, J, K. And here we put dx, dy, dz. And now we just put x cubed minus 3y squared x. The next component is minus y cubed plus 3x squared y. And this component, by the way, is actually 0. All this component is 0. Okay, so now I don't spend any time on that because I know that these two components are going to be 0 plus 0j plus k now. So k, you delete this and that, right? Derivative of this guy with respect to x is going to be 6xy minus, so we have to be careful. This is deleted, so 6xy. And then here, with respect to y, well, the minus plus 6xy. So this is equal to 12xy. So this is different from 0. So this vector field, in other words, is never, is not curve-free. There is rotation in this vector field. We know that. It's rotation. And it is rotation. So there is a comment. Z-axis, yes, that's correct. Very good. Okay, now let's go for divergence. So for divergence, Divergence is easy. I mean, this is the divergence of f is equal to ddx x cubed into 3y squared x plus ddy negative y cubed plus 3x2y. Okay, now what is this guy? Well, with respect to x, here we get 3x2, right? x2. This is minus 3y2. And then with respect to y, we get negative 3y2. And then plus 3x2. Okay. So that's not zero either. But you notice something. So this vector field is not carefree, is not divergence. But you notice something. If I had minus here, then both of these guys would be zero. So the first one would be zero and the second one. So, okay, so now let's look at question 2 then. Take this, you go on, and you notice that, well, this is equal to 0 in this case, with minus, this is equal to 0. I mean, minus or something. This is equal to 0. So this is carefree. So it's like a 2-for-1 problem, right? So it's 2 questions packed in one. So now IEF is irrotational. And as far as divergence goes, divergence is also 0 for that one, for the minus sign that I introduced. And also divergence of them. So here is a vector field that's both irrotational and incompressible. So this vector field is both, i.e. f. This f, remember I changed my vector field. This f is both irrotational and incompressible. Right? F is both irrotational and incompressible. Both conditions. And actually, water flow in rivers, if it's in a steady state, and if there are no viscosities, do you know what the flows or fluids that are non-viscous? What's the other name for them? They're called inviscid. Have you heard this before? No. Well, I'm not surprised you haven't done hydrodynamics. I didn't know it before I learned it either. So what's that? Oh, inviscid? Here is inviscid. It means non-viscous, no viscosity. This is perhaps maybe an older word, so inviscid. Anyhow, so inviscid or non-viscous steady state water flow in rivers is really modeled by a vector field, two-dimensional version, is vector field which is both irrotational and incompressible. So this situation is not theoretical at all. It's a very, very real life situation. It's a very real life situation. You see it everywhere. You can see it for different types of vectors. So basically, I think we are done with vector fields. So I want you to ask me some questions. Yeah. So what? ask me any questions except for assignments I'll do tomorrow. So don't ask those things. It gets me mad. Yeah. Okay. So home. Do you have any questions? Yeah. A really good exercise is to draw the flow lines for this vector field. So let me give you as an example. So because we found that, I mean, this vector field is not accidental. Look, it satisfies two very complicated equations. First of all, divergence is 0 and curl is also 0. If I ask you, create such a vector field, except for 0, I mean, it's very hard to construct a vector field which is both divergence free and curl free. But I can give you zillions of such vector fields if you give me for each of them maybe 1 minute to do calculation. I did some secret calculations there.
Yeah, I saw you're doing something with imaginary numbers.
Yes, yeah. that's the secret, right? Yeah. So do you know complex numbers? Yeah. So for those who know complex numbers, I tell you how to create lots of vector fields which are both. So what you do, for example, you can take this. Okay, so but before doing that, so here's another exercise. Draw the flow lines of the vector field F equal to x cubed minus 3y2x I plus or minus rather negative y cubed plus 3x2y. Okay. So what is the flow lines now? What we are looking at? What are the flow lines? Do you remember? I defined this concept in class. You remember? No? Yes.
Is it where like the vector field is tangent?
Yeah. So exactly. So we have to draw a system of lines. Just intuitively, you just look at system of lines. Whatever. We don't know. But the system of lines is such that through each point, there exists one line and only one line passing through that point. So basically what you do, you're dividing the whole plane into lines. You're chopping that into these kind of layers of lines. Okay, so you do that, and the property of this line should be that the vector field at this point is tangent to these lines at least. So that's so we have to find kind of flow lines for this. So how are you going to do flow lines in this case?
Well, you know it's irrotational and as well as divergence free.
Okay. Does it help? Well, I mean, no, I mean, that's true. It does help to some extent. But finding the system of lines, you remember, for these lines, I said that if you draw the equations like, so what did we know, for example, for gradients of something, some gradient vector fields? What did we know about those?
So it's tangent to the surface.
Yes, or tangent to the level curve, right? So in this case, if you can find some system of curves that are level curves of a function of two variables, then we are okay. Then we have found it. So the question is there a function which is such that these lines or these curves are going to be level curves of that function? We want to understand that. Is such a thing possible at all? Right? So are they going to be level curves for this? But now I ask you a question, because this is a very good problem. I ask you a question. Is this a gradient field or not? Is this vector field a gradient field? Is F a gradient field? I.e., is it true that F has a potential, right? I.e., does F has a function? Does it? So what is the answer? What would be the answer to this question? Does it have a potential function? Is it a gradient field? Is it a gradient? Yes. Why?
Because divergence is 0.
Because divergence is 0 and the vector field is defined over all plane, and topology is taken care of because there are no singularities, no holes, no bad points. So everything is okay in this case. The answer is yes. Yes. Since, I mean, among other things, this is divergence 0, right? So it has two properties, both care and divergence are 0. But I just use divergence at the moment. Yes, since divergence of that. Okay, now, so we know that, so there exists f of x and y such that gradient of f is equal to, such that, yes, gradient of little f is equal to cap f. So can you find this little f now? Let's go and find this little f. So what is the property of little f? Well, the potential has to satisfy these two equations. Fx has to be equal to fx, right? I mean, has to be equal to x cubed minus 3y2x, right? X cubed. So let me write it here like a good student. So f sub x is equal to x cubed minus 3y2x. And we have to solve these two systems. F sub y is equal to what? What is f sub y should be? Is y cubed minus 3x squared y, right? Y cubed minus 3x squared y. You see, don't forget about this minus sign here. It has to go inside. Otherwise, it's not. Okay, so I want you to solve this and find what is f. You have only 2 minutes. Because I told you have only 2 minutes, you have an advantage now, psychological advantage. You know that it's not such a difficult problem. If I told you go home and do it in 2 days, you would be like really in bad shape to start the problem. Okay, so find the potential first. So home, please also find the potential. Thank you. Did you find the potential? 2 minutes passed, yes. What did you find?
X4 over 4 plus Y4 over 4 minus 3Y2 X2 over 2 plus C.
That sounds right. Looks, yeah, I think that's correct. So let's do it together now. All right, so, well, I mean, this is just the first equation. Immediately tells you that you just take antiderivative of both sides, right? The first equation tells you that f of x and y, right, is equal to quarter of x4 negative 3 over 2 y2 x2. But then don't make the mistake of putting a constant there, because the constant depends on y, so it's a function of y now, right? Plus g of y. So then here you get f sub y, which is equal to negative 3 y2x plus g prime of y. That's equal to, now y cubed minus 3x squared y. That's equal to y cubed minus 3x2 y. Well, this 3y2x, 3y2x, what? 3 to respect to y, 3yx together. Anyhow, so yx2, this cancels with that. So g prime of y, you get indeed, yes, g prime of y, you get y cubed. So this finally gives you g of y. That's the constant, which is quarter by 4 plus constant. Okay, so then f of x and y is equal to f of x and y is equal to, what do we get? We have, well, we've got y quarter of x4, negative 3 over 2 y2 x2, plus quarter of y4, plus a constant. Now, this constant, the potential in constant is completely up to us. It's a matter of convenience what we choose, but let's just put it equal to 0 completely. Just make it equal to 0. There is no harm in doing it at this stage. Sometimes there is a harm in choosing the wrong constant, but here there is no harm. So it depends on situation. So that's equal to. Okay, so that's this. Then. So we haven't found flow lines, but we have found level curves such that the this vector field is actually orthogonal to that, right? So we have found. So if we draw the level curves of f of xy equal to some constant c, then we have a pretty good idea of the form of this vector field. And then f is orthogonal. It's not tangent, unfortunately. It's orthogonal. But I'll tell you how to find the other system as well. But let's just then f is orthogonal to this system of curves. Okay, so we have to draw these curves now. How are we going to do that? My God. Doesn't sound like a very easy problem. But let's, it's a trivial thing, really, but drawing it by just without any, trivial in terms of there are a lot of tools available now. So let's start. 1 quarter 4x4 minus 3 over 2 y2 x2 plus quarter y4 equal to some constant. So for example, let's put equal to 0, 1, minus 1. E.g., do you want to pull out your internet site and then check this, give it to the equation and see what's. There must be an applet who does these things.
I don't know one that draws level curves.
Oh, there are zillions. There are zillions. Just say draw the level curves for free online. It'll do it for you. I just came across this wonderful problem as I was lecturing. So that's the best way to. Yes.
Are we expected to find the potential from a?
Oh, absolutely, yeah. So the question is, are we expected to find the potential? Absolutely, yes. Of course. Well, potential shows your potential. So that's very important. No, I mean, finding potential is absolutely, actually vector potential also. You have to be able to find vector potentials.
Like, if you want to.
Yeah, can you pass it?
That's when it's 0.
So for 0, so for 0, you just found system of lines?
Yeah.
Oh, that's easy. Right. Okay, so for 0, wait a minute, doesn't make sense. These are just some straight lines.
Yeah.
It cannot be a straight line.
That's weird.
No, it cannot be. I mean, this equation, it's kind of, it's an interesting equation. Anyhow, we are at the end of the lecture, so that's okay. So do it at home, please. Use internet resources. To draw this level curves. I don't expect you to be able to draw the level curves that need some calculator or some program like Maker or something. But it's always a good idea to experiment with. So I try to remember this for myself. Wait a minute, I know why it was, so I know what happened. So this is x4 minus 6x2y2 plus y4. So no, but that doesn't make sense. x2 minus y2 squared, so 2x2 y2. So if you put it the other side, no, I think I'm getting somewhere. This is equal to 4x2 y2. But that's not unbelievable to have that. Okay, guys. So I see you on Monday. Have a good day.
Professor, I just have a quick question.
Yes.
So when you were deriving the potential in the last question, I didn't get where that g of y function came from.
Oh yes, that's a good question. I kind of emphasized while I was driving. You see, if this was a question in one variable calculus, then you had just derivative equal to something, right? Then what would you do? You would just end up with a constant, right? But here is a 2 variable, and that constant depends on y.
Right.
There's no reason to believe that the constant is independent of y, because for each y you have a problem to solve, right?
Yes.
We found a kind of system of primitive functions or integrations for each y. And there's no reason that different solutions for different y's should enjoy the same constant.
Right, yeah, that makes sense, I think.
So then as a result, we kind of guess and allow, in other words, that there should be a dependence of the constant on y. Because if you kind of reverse, if you think reversely, right? If that constant just depends on y, it's not a real constant, depends on y. Still, you get your equation satisfied, because the derivative of that thing with respect to x is 0. It's a function of y, right?
Right.
So that's always it's always important in these 2 variable things that then you get constant of integration to add, to allow g of y.
Okay, that helps a lot. Thank you.
Thank you. Yeah. Okay. Any other comments or questions? No. You want to leave? You can leave. I'm not holding you here. No. I mean, you can leave anytime. I mean, you're absolutely fine. Oh, you are very polite. Thank you. Thank you so much. Okay, guys. Thank you so much. So it seems there are no other questions. I just pause.